So hello, this is Galen Pickett, Physics 151, California State University, Long Beach, and we talked about the momentum principle in Chapter 2.2. Now Chapter 2.3 is where I want to go. So applying the momentum principle, the application that I want to focus on is this update form of the momentum principle. We're going to use a lot of, you get a lot of mileage out of that. But simultaneously, once we figure out how the momentum principle changes the momentum, we'll figure out how the velocity changes the position. So that is right here. Discussions on what is the average velocity, how to change position if you know what the velocity is. So, into the notes. So, where is the object? Now we've got an object that, just as we did in the last case, we've got it dropping for some amount of time, delta t. We know something about where it is when it's all done. I'll remind you of the result from the last problem. V final was equal to delta t times the weight as a vector divided by the mass. If we resolve this into the z components, so before I do that, let me just write this as triples of numbers. The final velocity has got 0 for its x component, 0 for its y component, but v final z for its z component. And that's equal to the scalar multiple of the weight vector, delta t divided by m, times the weight has got a component of 0 in the x direction, 0 in the y direction, and the magnitude of the weight points in the minus z direction. That's what that minus is sitting there for. So we have got that the final z component of the velocity is minus delta t divided by m times the magnitude of the weight force. If two vectors are equal, their z components have got to be equal. So I know what the velocity is, but I want to know where is the object now. So where is the object? How far has it fallen? What is this delta z? So again, let's look at the problem-solving rubric. The director says, well, the momentum principle is the thing that tells us what is the final velocity, v final. Once we know v final and v initial, we can find v average. So under, this is going to be an approximation, but under conditions in which the force changes at a constant rate, the average velocity is just the algebraic average of the initial and the final velocities. And once we have the average velocity, then we'll use the position update idea to tell us what our final is, and that will tell us how far the object has moved. That is the plan. So what do we know? We know our initial. That's where I put the origin when I made this diagram. I know v initial is equal to 0. I know delta t. I know the magnitude of the weight. That's, you take this object and you put it on a scale that reads newtons, and it tells you what its weight is. If it reads pounds, then you can convert pounds to newtons. What's unknown? Well, I do not know our final. Our final is not known, and as a vector even, that is the thing we're looking for. Circle the thing that is the target of the calculation. So that is what our final. I don't know what the average velocity is. It's not given in the statement of the problem. I don't know what the final velocity is. It's not given in the statement of the problem, although the momentum principle will help us figure out what it is. So it looks like we have three things that are unknown. They're each going to be pointing in the z direction. So I've got three quantities, but I've got 1, 2, 3 ideas. So I've got a plan that's coherent. And this, if you do this on an exam, that's 2 out of 2 points. 2 out of 2 points for having a coherent plan, 2 out of 2 points for having the list of the knowns, the unknowns, and circling the target. The investigator now takes over. That's the next role in your social homework groups. So, put the origin where the object is released. So, you need to be definite about that, or you can't even begin the problem. Let's say the z direction is upwards. So here our initial is 0, 0, 0 meters is our initial. our final is 0, 0, and I'll just write it as z final. Z final is going to be a negative number, but it's something. R final. V initial is equal to 0. V final is not known, but it's going downwards. This whole, so I've got, and this whole thing happens at a time delta t. So now, that is one point in identify as at least making a diagram with an origin, all the quantities labeled. That's 1 point out of the 2 points. Now we turn the plan from the director into ideas. So first is the momentum principle. The final momentum, which I'll write as m times v final, is equal to the initial momentum, which in this case is 0, plus delta t times the force from the surroundings, which is the weight vector. And that is what the momentum principle says. I'll just give that a number 1. The average velocity idea, as long as the velocity is changing at a constant rate while the force is a constant magnitude, we'll have v average is 1/2 v initial plus v final as vectors. So you add v initial and v final together, then you divide by 2. That is equation number 2. And then equation number 3 is the position update idea that tells us where the object is gone. R final, which we do not know, is equal to R initial, which is 0, plus delta t times v average. And those are the 3 fundamental ideas that will solve this problem. I've got 3 ideas and 3 unknowns, 3 equations, 3 unknowns. So I'm going to have a solution, and I can go on to execute. So execute, remember, we're looking for how far we've fallen. We're looking for R final. So the thing to do is always to solve the equations that don't have the R final in it. I want R final to be the last thing I solve for. That way I won't have to go back and back substitute. So equation number 1 tells me V final is equal to delta t weight divided by m. V final is a scalar multiple of the weight. Let's just check that the weight is a vector that points downwards. So V final is going to be parallel to the weight and will be also downwards. So there's a correct sign in that equation. I'm going to substitute this into equation number 2. So V average is equal to 1/2 the final velocity, it's the initial velocity, which is 0, plus the final velocity, which is delta t over m times the weight. I've used this expression here. That's where the V final is. I just substituted into equation number 2. So now I know what V average is. It is delta t divided by 2m times the weight. And now I can tell you from the position update idea number 3, R final. R final has components 0, 0, Z final. And that's equal to R initial, which is 0, 0, 0, plus delta t times, now V average, I'll write it out here. I'm just going to substitute it in, but I'm going to write it in its components. So I've got a scalar multiple out front, which is delta t divided by 2m, and the weight itself is 0, 0, and then minus w. So w is the magnitude of the weight vector. And now, this is equation number, so that was equation number 3. Now I've got a single unknown here. If I look at the z components of these equations, I get z final is equal to delta t squared over 2m times minus w, or minus weight divided by 2m times delta t squared. And that is the answer I get for how far it has fallen. So now we have to review this. You get 2 points if you get the right answer here. You get 0 points if you get the wrong answer. That's the standard of execution for the executive part. Skeptic review. First, we'll check the units of our expression for z final. I've got weight, mass, delta t squared. Notice that the 2 is dimensionless, so I don't even have to put its units in. The weight as units of newtons, the delta t as units of seconds, so I have 2 of those, and then the mass has units of a kilogram. So a newton is a kilogram meter per second squared. I then multiply that by the second times the second and divide by the kilogram. Kilograms cancel, seconds cancel, and I have meters. So my expression at least is some distance. There are no unknowns in my answer, so I have solved a problem. And now let's check. Z final, this is something you've probably seen before, minus 1/2 weight divided by mt delta t squared. This should look to you something like z is equal to minus 1/2 gt squared in a different kind of a problem, a constant acceleration kinematics deal. If you've taken a physics course before. And if you have not taken a physics course before, if you, in high school or so, then you may not have seen this constant acceleration idea. If you try to use one of these constant acceleration ideas, like saying at the beginning, z is equal to z0 plus v0zt plus 1/2 minus gt squared, if that's where you start off, there is no fundamental idea here. This method, it works. There's about six different equations you've got to remember, and that's not what this course is about. This course is not about remembering the details of, was I given a distance and a time, do I know what the final velocity is, which of these six different equations do I need to remember. The thing you need to remember is momentum principle, average velocity, and position update. Those three ideas, no matter what is given, what's known, what's unknown, gives the answer to all of these problems. Every projectile motion problem, this is the fundamental way to approach it. The momentum principle is always right. The average velocity idea, as long as we have forces that don't change in time, that is magnitude or direction, that's always right. And position update is always right. This is a fundamental line of reasoning that I want you to remember, and I will reward you on an exam for remembering.